In the vast expanse of space, beyond the reaches of our solar system, two intrepid spacecraft continue their relentless journey, carrying humanity's message into the cosmos. Voyager 1 and Voyager 2, launched in 1977, have traversed billions of miles, exploring uncharted territories and making groundbreaking discoveries. These iconic probes, now well into their interstellar missions, face a unique challenge. Their computers, relics of the 1970s, are running on just 70 kilobytes of memory. Yet, despite these limitations, NASA has managed to keep these distant sentinels alive, sending software updates across vast distances of space to ensure their continued operation. As a result, in the blackness of space, billions of miles from home, the Voyagers crossed the threshold, and it's giving humans new insight to some of the big mysteries of our solar system. In a world-shattering revelation, the twins just revealed that interstellar space even weirder than expected. Join us as we dig deep into Voyager's impossible discovery after 46 years in space. Insofar as we esteem the creations that last, Homer's Odyssey, the bridge still standing, enduring love, let us now praise the twin Voyager space probes, launched 46 years ago and currently departing the solar system to drift forever among the stars. Each about the size and weight of a subcompact automobile, the Voyagers epitomize 1970s high-tech. Their computers are weaker than those in today's digital watches, their analog TV cameras more primitive than the ones that shot Laverne and Shirley, but they made history at every planet they reconnoitered, confirming, as Voyager chief scientist Ed Stone put it, that nature is much more inventive than our imaginations. Jupiter, which looks serene through a telescope, was shown by Voyager to have hundreds of raging hurricanes, a glowing aurora at the North Pole, and 3 thin rings. Saturn's rings, previously countable on the fingers of one hand, turned out to include thousands of ringlets and seemingly braided components that theorists had assumed were impossible. Active volcanoes, formerly found only on Earth, turned up in abundance on Jupiter's satellite Io and, astoundingly, on Neptune's Triton, where nitrogen geysers were observed erupting at 40 degrees above absolute zero on the Kelvin scale. 2 of the solar system's most promising environments for finding alien life, Jupiter's icy moon Europa and Saturn's Enceladus, were unveiled by the Voyager mission. Their cores palpitated and heated by tidal interactions. Europa and Enceladus appear to sustain vast, briny oceans beneath the ice, where living organisms might thrive. Perhaps the most poignant gesture of the Voyager mission was its final parting salute to its place of birth. The portrait of the Sun's family of planets taken in early 1990 included an image of Earth. Carl Sagan, a member of the Voyager imaging team and the captain of the small team that had produced the Golden Record, had proposed this image to the Voyager project in 1981. He eventually called it, appropriately, the pale blue dot. His motivation is expressed in his book of the same name, in which he describes wishing to continue in the tradition, begun by the famous Earthrise images of the Apollo program, referring specifically to the one taken from the surface of the moon by Apollo 17. Then, he continues, "It seemed to me that another picture of the Earth, this one taken from 100,000 times farther away, might help in the continuing process of revealing to ourselves our true circumstance and condition." It had been well understood by the scientists and philosophers of classical antiquity that the Earth was a mere point in a vast encompassing cosmos, but no one had ever seen it as such. Here was our first chance. On August 25, 2012, NASA's Voyager 1 spacecraft was 11 billion miles or 18 billion kilometers from the Sun, and scientists determined that the venerable spacecraft had crossed the boundary between the Sun's influence and the interstellar medium. Now still going and still sending back data, Voyager 1 and its twin Voyager 2, which joined it in interstellar space in 2018, continue to conduct groundbreaking science. Both Voyagers are now so far from Earth that a one-way radio signal traveling at the speed of light takes almost 22.5 hours to reach Voyager 1 and near 19 hours to catch up with Voyager 2. Every day, they move away by another 3 to 4 light seconds. Their only link to Earth is NASA's Deep Space Network, a trio of tracking complexes spaced around the globe that enables uninterrupted communication with spacecraft as Earth rotates. As the Voyagers recede from us in space and time, their signals are becoming ever fainter. Earth is a noisy place. Radios, television, cell phones, everything makes noise. And so it gets harder and harder to hear these tiny whispers from the spacecraft. Faint as they are, those whispers still meet astronomers' expectations of what the Voyagers would find as they entered the interstellar phase of the mission. A big science endeavor that consumed some 10,000 work years, the mission has been described as one of the greatest voyages of exploration ever conducted by our species. However, it almost didn't happen. The Voyager mission arose from a happy accident of celestial mechanics. First, Michael Minovich showed that a spacecraft could steal velocity from a planet and use it to accelerate away from the sun. Gary Flandreau then applied that logic and showed that probes launched in the late 1970s and 80s could benefit from a rare geometric lineup of the outer planets, skipping world to world on gravitational arcs. Neptune, at the solar system's ragged edge, was suddenly reachable in a dozen years rather than 30. But if the chance was missed, another wouldn't arise until the 22nd century. NASA seized on the opportunity, but shrinking budgets made a grand tour of the outer solar system too expensive. So, the mission was downsized to a $250 million visit to Jupiter and Saturn. But researchers held out hope for a Uranus and Neptune detour. Theoretically, if Voyager 1 worked at Jupiter and Saturn, Voyager 2's trajectory could still be tweaked to visit them. With all options open, Voyager 2 launched on August 20th, 1977 on a long, slow trek into the unknown. Voyager 1 followed on September 5th on a shorter, quicker route. Both spacecraft bristled with scientific gear: cameras, infrared and ultraviolet spectrometers, sensors to map charged particles, cosmic rays and plasmas, a photopolarimeter, and a magnetometer. Nuclear-powered, the Voyager crafts were expected to survive for 5 years. But with some luck and power budget managing, they've exceeded that goal tenfold. Now, renowned as a daring, endless trek to the outer planets and beyond, the Voyager mission became iconic over the years in its scope and meaning. More rite of passage than expedition, more mythic than scientific. The extraordinary images of alien worlds never before seen, and the precognitive sense of being there that they evoked connected laypeople the world over to Voyager's historic pilgrimage into the unknown, with eternity the final port of call. It was not folly to feel that the mission would gift us all a measure of immortality. The fabled golden record of Voyager heightened the fascination. The two Voyagers each carried a phonograph record of images, music, and sounds, representative of our planet, including spoken greetings in 55 languages to any intelligent life form that might find them. This was a message from planet Earth vectored into the Milky Way, a hopeful call across space and time to our fellow galactic citizens. It thrilled to think that news of us and our home planet might be retrieved by some extraterrestrial civilization, somewhere and sometime in the long future of our galaxy. Because of its never-ending journey, its dazzling scientific discoveries in the solar system, and its human-forward countenance, to participants and onlookers alike, Voyager became symbolic of our acute longing to understand our cosmic place and the significance of our own existence. Up to now, thanks to the twins, humankind has spent more than a decade exploring interstellar space. But as giving humans new insight into some of the big mysteries of our solar system, NASA probes stunned the whole world by revealing that interstellar space even weirder than expected. To make sense of shocking findings, it helps to know that the sun isn't a quietly burning ball of light. Our star is a raging nuclear furnace hurtling through the galaxy at about 450,000 miles an hour as it orbits the galactic center. The sun is also rent through with twisted, braided magnetic fields, and, as a result, its surface constantly throws off a breeze of electrically charged particles called the solar wind. This gust rushes out in all directions, carrying the sun's magnetic field with it. Eventually, the solar wind smashes into the interstellar medium, the debris from ancient stellar explosions that lurks in the spaces between stars. Like oil and water, the solar wind and the interstellar medium don't perfectly mix, so the solar wind forms a bubble within the interstellar medium called the heliosphere. Based on Voyager data, this bubble extends about 11 billion miles from the sun at its leading edge, surrounding the sun, all 8 planets, and much of the outer objects orbiting our star. Good thing, too. The protective heliosphere shields everything inside it, including our fragile DNA, from most of the galaxy's highest energy radiation. The heliosphere's outermost edge, called the heliopause, marks the start of interstellar space. Understanding this threshold has implications for our picture of the sun's journey through the galaxy, which in turn can tell us more about the situations of other stars scattered across the cosmos. As Voyager project scientist Ed Stone said, "We are trying to understand the nature of that boundary, where these two winds collide and mix. How do they mix, and how much spillage is there from inside to outside the bubble, and from outside the bubble to inside?" Scientists got their first good look at the heliopause on August 25, 2012, when Voyager 1 first entered interstellar space. What they began to see left them scratching their heads. For instance, researchers now know that the interstellar magnetic field is about 2 to 3 times stronger than expected, which means, in turn, that interstellar particles exert up to 10 times as much pressure on our heliosphere than previously thought. According to heliophysicist Patrick Coyne, a program scientist at NASA headquarters, it is our first platform to actually experience the interstellar medium, so it is quite literally a pathfinder for us. But for all that Voyager 1 upended expectations, its revelations were incomplete. Back in 1980, its instrument that measured the temperature of plasmas stopped working. Voyager 2's plasma instrument is still working just fine. So when it crossed the heliopause on November 5, 2018, scientists could get a much better look at this border. For the first time, researchers could see that as an object gets within 140 million miles of the heliopause, the plasma surrounding it slows, heats up, and gets more dense. And on the other side of the boundary, the interstellar medium is at least 54,000 degrees Fahrenheit, which is hotter than expected. However, this plasma is so thin and diffuse, the average temperature around the Voyager probes remains extremely cold. In addition, Voyager 2 confirmed that the heliopause is one leaky border, and the leaks go both ways. Before Voyager 1 passed through the heliopause, it zoomed through tendrils of interstellar particles that had punched into the heliopause like tree roots through rock. Voyager 2, however, saw a trickle of low-energy particles that extended more than 100 million miles beyond the heliopause. Another mystery appeared as Voyager 1 came within 800 million miles of the heliopause, where it entered a limbo-like area in which the outbound solar wind slowed to a crawl. Before it crossed the heliopause, Voyager 2 saw the solar wind form an altogether different kind of layer that, oddly, was nearly the same width as the stagnant one seen by Voyager 1. According to Coyne, that is very, very weird. It really shows us that we need more data. Solving these puzzles will require a better view of the heliosphere as a whole. That's also why NASA has managed to keep these distant sentinels alive by sending software updates across vast distances of space to ensure their continued operation. But updating Voyager's software is a daunting task, akin to performing brain surgery on a patient located 15 billion miles away. The process involves sending new code to the spacecraft's computers, which are designed to operate on machine language, the most basic form of programming. This means that the code must be written in a language that can be directly understood by the hardware, without the aid of an operating system or any fancy programming tools. To overcome these challenges, NASA engineers rely on a combination of ingenuity and resourcefulness. They use assembly language, a low-level programming language that closely resembles machine code, to write the update instructions. This allows them to control the hardware directly and ensure that the code is as efficient as possible. Additionally, they employ pseudocode, a simplified set of commands, to automate repetitive tasks without wasting precious memory. The software updates sent to Voyager are not just patches to fix bugs, they are lifelines that keep these spacecraft alive. Over the years, these updates have addressed various issues, from restarting malfunctioning components to correcting faulty bits of memory. In one instance, a software update saved Voyager 1 from a potential disaster when a piece of hardware failed. The update triggered a fail-safe mechanism, allowing the spacecraft to continue its mission. The ability to update Voyager's software remotely is a testament to NASA's engineering expertise and the resilience of these spacecraft. It demonstrates that even with outdated technology, innovation and resourcefulness can overcome seemingly insurmountable obstacles. In future, as Voyager 1 and Voyager 2 venture deeper into interstellar space, the challenges of keeping them operational will only grow. However, NASA remains committed to these missions, determined to extend the lives of these valuable probes for as long as possible. Software updates will continue to play a crucial role in this endeavor, ensuring that these pioneers of space exploration continue their remarkable journey. The story of Voyager's software updates is a reminder of the power of human ingenuity and the enduring legacy of space exploration. It is a testament to our ability to overcome seemingly insurmountable obstacles and push the boundaries of what is possible. As Voyager continues its journey into the unknown, we can only imagine the discoveries that await, made possible by the dedication and brilliance of those who keep these distant sentinels alive. In addition to making groundbreaking discoveries, the Voyager mission helped scientists determine what merited deeper exploration. The mission revealed Jupiter to be an incredibly complex planet, thus spurring NASA to launch the Galileo mission in 1989 and the Juno mission in 2011. The Voyager probes' work also helped to inspire the iconic Cassini mission to Saturn. As Jonathan Lunine, a planetary scientist and physicist at Cornell University who is working on the Juno, Europa Clipper, and James Webb Space Telescope missions, said, Voyager 1's close flyby of Titan was the catalyst for the wonderful Cassini mission to Saturn and its Huygens probe. The Huygens probe landed on the surface of Titan in 2005 and sent back an incredible video. Voyager 2 has also been a catalyst for investigations into the role of the ice giant planets, not only in the solar system, but also in distant star systems, since most of the exoplanets found so far are roughly the size of Neptune and Uranus. NASA has spent decades following up on the Voyager missions, and those efforts continue today. The space agency's Dragonfly mission will reach Titan, Saturn's largest moon, in 2034, while Europa Clipper will study Jupiter's ocean moon, first imaged by Voyager, starting in 2030. In April, the National Academy's Planetary Science Decadal Survey recommended that NASA send a $4.2 billion Uranus orbiter and probe mission to unveil the mysterious ice giant planet and its moons in the 2040s. It's the latest mission that's a direct consequence of Voyager 2's brief visit to the Uranus system in January 1986. According to Lunine, Voyager 2's flyby of Uranus was a bullseye. It went directly through the plane of the moon's orbits because of the orientation of Uranus's axis to the sun. That made it unlike flybys at other planets, where the probes were able to visit one moon after another. Voyager 2 got very brief images from these moons, so they're largely unexplored. Ariel and Miranda in particular are thought to be ocean worlds, and so would be specifically targeted by the Uranus orbiter and probe. It's been 45 years since the launch of Voyager 1 and Voyager 2, and here we are now. Finally talking about a Uranus orbiter and probe mission, Blue 9 said. It seems like a long time because these missions take so long to conceive of, fund, build, launch, and execute, but it all comes from the intriguing peaks that we got from Voyager 2. Both Voyager 1 and Voyager 2 still communicate with NASA's Deep Space Network, which itself was created to communicate with Voyager 2 at Uranus and Neptune, receiving routine commands and occasionally transmitting data to Earth. Estimatios Krimigas, principal investigator for the Voyager 1 and 2 probes and the Voyager interstellar mission, said during a news conference held at Kiospar 22 in July, "We are still getting data from Voyager. We're looking forward to getting data for probably another 5 or 6 years." Around the mid to late 2020s, the probe's scientific instruments will be entirely switched off, and eventually the spacecraft will go cold and silent, but their journeys into interstellar space will continue indefinitely. As Krimigas, who is in his 80s, said, "My motto is, I want to be here after Voyager passes on, but I'm not sure that's going to happen." In around 300 years, Voyager 1 and 2 will enter the Oort cloud, the sphere of comets surrounding the solar system. About 30,000 years later, they'll exit the neighborhood and silently orbit the center of the Milky Way for millions of years. Their scientific work may be almost over, but the Voyager spacecraft have only just begun their journeys into the cosmos. Notably, while the Voyagers continue on their unimaginable journey, Hubble, NASA's nearly 33-year-old observatory, also has just shown that it is still in the game. The forbidden light of a distant spiral galaxy shines brightly in a new image from the Hubble Space Telescope. Located about 275 million light-years from Earth, the galaxy, called MCG 01244014, has two prominent, well-defined spiral arms and an energetic glowing core known as an active galactic nucleus, or AGN for short. The galaxy is seen face-on with its arms creating a nearly perfect circular shape. MCG 01244014 is classified as a Type II Seyfert galaxy, which is one of the two largest groups of active galaxies scientists know of, along with quasars. Seyfert galaxies exhibit a characteristic bright core, but are less detectable when compared to quasars, whose incredibly luminous AGNs can outshine the entire host galaxies within which they reside, according to a statement from the European Space Agency. Seyfert galaxies can also be further categorized based on the intensity of light being emitted from their active cores. Depending on the wavelengths of light, or spectra, Seyfert galaxies are classified as either Type 1 or Type 2. The latter emit spectral lines associated with so-called forbidden emissions, given they should not exist according to certain rules of quantum physics. As European Space Agency's officials said in the statement, to understand why emitted light from a galaxy could be considered forbidden, it helps to understand why spectra exist in the first place. Spectra look the way they do because certain atoms and molecules will absorb and emit light very reliably at very specific wavelengths. Electrons, the tiny particles that orbit the nuclei of atoms, lose or gain specific amounts of energy, which correspond to certain light wavelengths being absorbed or emitted. However, certain spectral emission lines are considered to be forbidden because they are observed in space but do not occur under normal conditions on Earth. Quantum physics is complex, and some of the rules used to predict it use assumptions that suit laboratory conditions here on Earth, European Space Agency's officials said in the statement. Under those rules, this emission is forbidden, so improbable that it's disregarded. But in space, in the midst of an incredibly energetic galactic core, those assumptions don't hold anymore, and the forbidden light gets a chance to shine out towards us. Indeed, the bright light from MCG 012414 shines radiantly in the new Hubble photo, which was taken using the telescope's advanced camera for surveys. The spiral galaxy appears in the center of the image, with two large bright stars in the foreground, one blue and one red, positioned directly above the galaxy itself. Several more distant galaxies are scattered across the otherwise pitch-black backdrop of space. ESA released the new Hubble photo online on December 18th.
A 5,000-pound satellite is plummeting toward Earth, and its fiery descent could leave debris scattered across the planet. The European Space Agency's ERS-2 satellite is making an uncontrolled re-entry, with chunks of its 2.3-ton mass likely to survive the intense plunge through the atmosphere. As scientists predict its fall with a margin of uncertainty, the world watches and wonders, where will the remnants of this celestial titan land, and what implications will it have for our understanding of space debris management? Background on ERS-2 and its mission ERS-2 was launched on April 21, 1995, as part of ESA's mission to monitor environmental changes and gather data on the Earth's surface and atmosphere. It carried an array of sophisticated instruments, including the Advanced Synthetic Aperture Radar, ASAR, a radar altimeter, and various sensors for measuring sea surface temperature, ocean surface winds, and atmospheric conditions. Over its operational life, ERS-2 provided invaluable data that contributed to numerous scientific studies and practical applications such as climate monitoring, disaster response, and maritime surveillance. Predicting the re-entry. The exact time and location of ERS-2's re-entry are subject to significant uncertainty due to the complex interplay of factors influencing its descent. As of the latest prediction issued by ESA's Space Debris Office, the satellite is expected to re-enter the Earth's atmosphere at approximately 12:05 p.m. EST, 1541 GMT, on Wednesday, February 21st, with a margin of error of plus 1.44 hours. This uncertainty primarily stems from the variable effects of solar activity, which alters the density of the Earth's atmosphere and consequently affects the drag experienced by the satellite. Atmospheric re-entry dynamics. Re-entry dynamics involve the interaction between the spacecraft and the atmospheric layers it traverses. As ERS-2 descends, it encounters increasing atmospheric density, leading to rapid deceleration and intense heating due to frictional forces. This process, known as ablation, causes the spacecraft's exterior to heat up and shed material. For most satellites, this results in the complete disintegration of the structure before reaching the Earth's surface. However, certain components, especially those with high melting points and structural integrity, can survive the descent. Survivability of ERS-2 components. Simona Elena Nichiteanu from ESA's European Space Operations Center, ESOC, indicated that between 10% and 20% of the satellite's mass might survive re-entry. The heaviest and most robust components, such as fuel tanks, internal support panels, and the synthetic aperture radar, SAR antenna, are most likely to endure the fiery descent. The survival of these components raises important questions about the potential hazards posed by falling debris and the need for effective tracking and mitigation strategies. Impact, prediction, and potential hazards. The primary challenge in managing re-entering space debris lies in accurately predicting the impact zone. Given that the Earth is predominantly covered by oceans, there is a high probability that surviving fragments of ERS-2 will splash down into the sea. However, the possibility of debris reaching populated areas cannot be entirely ruled out. This necessitates continuous monitoring and coordination with global space agencies to issue timely warnings and take precautionary measures. Orbital debris, management and regulation. The uncontrolled descent of ERS-2 serves as a stark reminder of the ongoing issue of space debris. With thousands of defunct satellites and spent rocket stages orbiting the Earth, the risk of collision and subsequent fragmentation increases, leading to the generation of more debris. This Kessler syndrome, a scenario where the density of objects in low Earth orbit, LEO, is high enough to cause a cascade of collisions, poses a significant threat to both active satellites and manned space missions. Michael Runnels, an assistant professor of business law at California State University, Los Angeles, emphasizes the need for enforceable orbital debris regulations. The absence of stringent regulatory frameworks means that many satellites are launched without adequate deorbit plans, increasing the likelihood of uncontrolled re-entries. Effective regulation would require satellite operators to design spacecraft with end-of-life disposal mechanisms, such as controlled re-entry or transfer to a graveyard orbit. Technological solutions for debris mitigation. Several technological solutions have been proposed and are under development to address the space debris problem. These include active debris removal, ADR techniques, such as robotic arms, nets, harpoons, and laser ablation. Each method presents its own set of technical and economic challenges, but the overarching goal is to reduce the number of debris objects in orbit and prevent future accumulation. For instance, ESA's ED-orbit mission aims to demonstrate the feasibility of capturing and deorbiting a defunct satellite using a robotic arm. Similarly, Japan's Aerospace Exploration Agency, JAXA, is exploring the use of electrodynamic tethers to reduce the orbital lifetime of debris. These innovative approaches, coupled with international cooperation and regulatory oversight, are crucial for ensuring the long-term sustainability of space activities. Case study: ERS-2's operational legacy. ERS-2's contribution to environmental monitoring and Earth observation has been significant. During its operational period, the satellite provided continuous data that enhanced our understanding of climate change, oceanography, and atmospheric science. The SAR instrument, in particular, enabled high-resolution imaging of the Earth's surface, facilitating studies on deforestation, urbanization, and natural disasters. The data collected by ERS-2 has been used in various applications, such as monitoring ice cover in polar regions, assessing the impact of oil spills, and tracking the movement of tectonic plates. This legacy underscores the importance of satellite missions in advancing scientific knowledge and informing policy decisions related to environmental protection and disaster management. Future implications and research directions. The re-entry of ERS-2 highlights several areas for future research and development in space debris management. These include improving predictive models for re-entry trajectories, enhancing tracking capabilities for small debris objects, and developing more robust materials and designs for spacecraft to minimize the risk of fragmentation. Furthermore, there is a need for comprehensive studies on the long-term effects of space debris on the orbital environment and the potential risks to both space-based and terrestrial infrastructure. Collaborative efforts among spacefaring nations, coupled with advancements in technology and regulation, will be essential in addressing these challenges and ensuring the safe and sustainable use of outer space. Conclusion. The uncontrolled re-entry of ESA's ERS-2 satellite serves as a poignant reminder of the complexities and risks associated with space exploration. As the 2.3-ton spacecraft descends towards Earth, it brings into sharp focus the need for effective space debris management and regulatory oversight. While technological advancements offer promising solutions, international cooperation and robust regulatory frameworks are critical for mitigating the risks posed by space debris and ensuring the sustainable exploration of outer space. The scientific community must continue to monitor and study re-entry events like that of ERS-2 to improve our understanding of orbital dynamics and the behavior of space debris. This knowledge will be instrumental in developing strategies to protect both space assets and human life on Earth from the potential hazards of re-entering spacecraft. As we venture further into the cosmos, the lessons learned from ERS-2 will guide us in safeguarding our planet and ensuring the responsible use of space for future generations. Unveiling the mysteries, James Webb Space Telescope's revelations on concealed exomoons, orbiting failed stars. In the vast expanse of the cosmos, where darkness intertwines with intrigue, the James Webb Space Telescope, JWST, emerges as a sentinel of exploration, peering into the enigmatic depths of the universe. Recent discoveries made by the JWST have unearthed a trove of revelations, challenging our perceptions of celestial bodies known as failed stars, and hinting at the presence of clandestine exomoons in their orbit. Initially, these revelations confounded astronomers, casting shadows of uncertainty over their understanding of the cosmos. Yet, as they delved deeper into the data, their bewilderment transformed into a fervent curiosity, fueled by the prospect of uncovering the universe's hidden truths. Harnessing the unrivaled capabilities of the James Webb Space Telescope, astronomers made a groundbreaking discovery: the detection of methane emissions emanating from a brown dwarf, colloquially known as a failed star. This revelation sent shockwaves through the scientific community, igniting speculation about the nature of these desolate worlds and the mysteries concealed within their veiled atmospheres. The presence of methane on the brown dwarf hinted at the existence of aurorae, celestial spectacles typically associated with planetary magnetospheres. Furthermore, researchers postulated the existence of an undiscovered exomoon orbiting the brown dwarf, adding an additional layer of intrigue to an already captivating narrative. The discovery of methane emissions on the brown dwarf defied conventional wisdom, as these frigid and isolated worlds were thought to lack the necessary conditions for methane to emit infrared light. This anomaly sparked a re-evaluation of existing theories and spurred a renaissance in our understanding of the atmospheric dynamics of failed stars. These groundbreaking revelations emerged from an exhaustive JWST program aimed at scrutinizing 12 brown dwarfs, each harboring its own mysteries waiting to be unraveled. The data suggested that these failed stars could generate aurorae reminiscent of Earth's northern and southern lights, as well as those observed on gas giants like Jupiter and Saturn. The absence of a nearby stellar companion raised tantalizing questions about the origins of the polar lights enveloping these solitary brown dwarfs, hinting at the presence of a concealed active moon. One of the focal points of the study was the enigmatic brown dwarf known as Quicep J193518, Phi 9 154620 W1935, situated 47 light-years from Earth. While the mass of W1935 remained poorly constrained, ranging from 6 to 35 times that of Jupiter, its surface temperature hovered around 400 degrees Fahrenheit, 204 degrees Celsius, a temperature range typically associated with earthly ovens rather than celestial bodies. Jackie Faherty, the team leader and senior education manager at the American Museum of Natural History, expressed initial bewilderment, followed by unbridled excitement at the discovery of methane emissions on the brown dwarf. The unexpected nature of these findings underscored the transformative power of scientific inquiry and the allure of unraveling the universe's deepest mysteries. The investigation delved into the fundamental mechanisms underlying the formation of failed stars, shedding light on their enigmatic nature and the forces that govern their existence. Brown dwarfs earned their moniker as failed stars due to their inability to sustain nuclear fusion reactions in their cores, a defining characteristic of main sequence stars. Despite originating from collapsing clouds of gas and dust like their stellar counterparts, brown dwarfs lack the requisite mass to initiate the fusion of hydrogen into helium, relegating them to a liminal state between planets and stars. As Faherty and her colleagues scrutinized several brown dwarfs with the JWST, they observed a peculiar anomaly in W1935, the presence of methane, a substance typically associated with giant planets rather than failed stars. Modeling studies revealed that W1935 exhibited a phenomenon known as temperature inversion, where the atmosphere grows colder at deeper levels, a feature more commonly observed in planets orbiting stars with external heat sources. Ben Birmingham, a team member and scientist at the University of Hertfordshire, expressed astonishment at the model's prediction of temperature inversion on W1935, catalyzing a quest to unravel the mystery of its origins. The team turned their gaze toward the gas giants of our solar system, Jupiter and Saturn, which exhibit similar methane emissions and atmospheric temperature inversions attributed to aurorae. By drawing parallels between the findings on W1935 and the auroral displays on Jupiter and Saturn, Faherty and her team hypothesized that the JWST had detected aurorae surrounding the brown dwarf. However, the absence of a host star to generate stellar winds raised questions about the driving force behind W1935's auroral activity. Solar wind, The stream of charged particles emitted by the sun serves as the primary driver of aurorae on planets like Jupiter, Saturn, and Earth. Yet, with no nearby star to produce stellar winds, the conventional explanation for auroral activity seemed inadequate. Nevertheless, the aurorae on Jupiter and Saturn exhibit a secondary driver: charged particles from their active moons, such as Jupiter's volcanic moon Io and Saturn's geyser-spewing moon Enceladus. The presence of aurorae around W1935 hinted at the possibility of an active moon orbiting the brown dwarf, offering a tantalizing glimpse into the hidden dynamics of these enigmatic celestial bodies. Despite these tantalizing clues, scientists acknowledge the need for additional evidence to confirm the existence of a moon orbiting a brown dwarf, a feat never before observed. Until then, the initial findings serve as a testament to the transformative impact of the JWST, which has revolutionized our understanding of the cosmos since its launch in the summer of 202. Faherty concluded by emphasizing the unpredictable nature of astronomical exploration, where every observation holds the potential for groundbreaking discoveries. The detection of methane emissions on W1935, while initially unexpected, underscores the importance of remaining vigilant and open to the unexpected in the pursuit of scientific knowledge. As the JWST continues to unravel the mysteries of the universe, astronomers remain poised on the brink of discovery, eager to explore the uncharted territories of space and unlock the secrets hidden within the cosmos. With each new observation, the boundaries of our understanding expand, revealing the vast and wondrous complexity of the universe that surrounds us. The recent discoveries made by the James Webb Space Telescope, JWST, about failed stars underscore the importance of maintaining an open-minded attitude and being ready to embrace the unexpected in the journey of space exploration. The detection of methane emissions on brown dwarfs has sparked a revolution in our understanding of these stars, raising new questions and opening new doors for exploration in the future. Continuing to pursue studies and observations of the universe with an open mindset will help us expand the boundaries of knowledge and uncover the mysteries of the cosmos surrounding us. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.